Hello students, welcome to the part 2 of the gas chromatography. We have discussed in the part 1 the gas chromatography introduction, principle, types, various components of the chromatography we have discussed like carrier gas, injection port, column, various types of the column. In this part, we move further. In this lecture, we are going to cover the types of the various detectors used in the gas chromatograph, the gas chromatograph instrument, how it works, what is the analysis, and the applications of the gas chromatography. What is the learning outcome of this lecture? You will be able to understand completely the gas chromatography by covering the types of the detectors, the instrumentation part, its working, analysis, and the applications. Now we talk about the detectors used in the gas chromatograph. The eluted solute particles along with the carrier gas exit from the column and enter to the detector. And the detector role is that it produces the electrical signals which is proportional to the concentration of the components of the solute. Depending on the concentration of the component which is present in the sample or the solute, it produces the electrical signals, and these signals are amplified and recorded as the peaks at the different time intervals on the chromatograph. So we get the chromatograph along with these peaks which are amplified. Now we see the properties of an ideal detector. The detector which is used in the gas chromatograph should contain these properties. It should be sensitive. Sensitive means for a little amount of the component, it could be identified and produce the signal for a little concentration. It operates at high temperature. That should be maximum up to 400 degrees centigrade. It is stable and reproducible. It should give the linear response, not the complex response. It should have a simple response. Wide dynamic range. Fast response should be there. Should be simple, reliable, non-destructive. Should not destroy. Uniform response to all the analytes. So these are some properties which can be said the ideal properties of the detector to be used in the gas chromatograph. Now we talk about various types of the detectors used in the gas chromatograph. The first detector is TCD, that is thermal conductivity detector. It is also called the hot wire detector and catharometer. It is made up of tungsten alloy wire. It is based upon the fact that heat lost from a filament depends upon the thermal conductivity of the stream of surrounding gas as well as the specific heat of the sample. What's the change in the thermal conductivity? It record and give the signal according to that. So the change in the thermal conductivity, it gives the signal TCD. It is very simple, inexpensive and non-destructive detector. It is also called universal detector. Its sensitivity is 10 to the power minus 9 grams. Understood? When only the carrier gas flows, the heat loss to the metal block is constant and the filament T remain constant when only the carrier gas flows. No change occurs. But when an analyte species flows, it goes for producing the thermal conductivity change. Thus, the resistance changes are sensed by the Wheatstone bridge arrangement, which is there inside the detector. The imbalance between the control and the sample filament temperature is measured and the signal is recorded. So, it detect on the basis of the thermal conductivity change, which produces the change in the resistance, which causes the signals to produce. So that is recorded. What are the advantages of the TCD and the disadvantages of the TCD? The TCD is a simple and inexpensive detector. It is durable and possesses the long life. It produces the accurate results. It is non-selective, hence it is known as universal detectors. What's the limitation? It is having low sensitivity, that is 10 to the power minus 9 gram, affected by the fluctuation in the temperature and the flow rate. The second detector is ECD, the molecules of the compound which possesses the affinity for the electrons. So on the basis of the difference in the electron absorbing capacity, this difference is utilized by this detector for the identification of the compound. In this detector, there is a foil which is made up of radioactive metal, that is nickel 63, which emit the beta particles. It's a beta emitter, radioactive metal. It is placed inside the Teflon coated cell, which is also contain the electrode, cathode and the anode. In the absence of the organic species, the produced electron migrate towards the positive electrode and produce a certain constant standing current in the absence. But when a sample eluent is present, it captures the electron, elute from the column, and there is a drop in the constant current. So when only the gas is flowing through this detector, so no, a constant current produces, but when your organic compound is there in the gas, it captured the electron on the basis of the electron absorbing capacity. There causes the decrease in the current, and the potential across the two electrodes is adjusted to collect all the ions and that steady saturation current which goes on recording. But its sensitivity is 10 to the power minus 9. Its sensitivity is 10 to the power minus 9 to 10 to the power minus 12 grams. Okay. This is having the sensitivity of grams. ECD. Now we see the advantages and the disadvantages of the ECD. It is highly selective, highly sensitive for the detection of the compounds like halogens, quinones, peroxides, nitrites. It is non-destructive detector. Its sensitivity is more than TCD and FID. TCD sensitivity is 10 to the power minus 9 grams, and of the FID it is 10 to the power minus 11 gram. And ECD is having the sensitivity 10 to the power minus 9 to 10 to the power minus 12. What's its disadvantages? Least sensitive to the compound whose molecules had negligible affinity for the electron, because the principle involved on the basis of the electron absorbing capacity it is detecting. So if the compound is having negligible affinity towards the electron, it is not possible for detecting those compounds. The carrier gas should be pure form like the pure nitrogen. It should be of very pure form, otherwise it should not give the good results. Now the third detector is FID, that is flame ionization detector. This employs the hydrogen flame which is maintained in a cylindrical jet made up of platinum or the quartz. The effluent when come to the detector after passing through the column with the helium or the nitrogen gas, it goes on burning under this flame and get ignited, undergo pyrolysis. It goes for burning and produce the ions. For detection of these ions, two electrodes are used which provide the potential difference. The ion produced are repelled by the positive electrode and hit the collector plate, and the current produced in doing so, that is recorded, amplify and recorded. So in this detector, the compound which is used or the sample which is used to analyze, it is burnt under the hydrogen flame to produce the ions, and the ions detected by the electrode generating the potential difference, and when this difference occur, on the basis of that the current goes on producing, which is recorded. So this is the diagram of FID in which the hydrogen flame is maintained under this platinum and the quartz plate. Two electrodes are there which generates the potential difference on producing the ions, and which goes on producing the current which is recorded. The next detector is FPD, that is flame photometric detector. It is a highly selective detector which is responsive to only the compounds containing sulfur or the phosphorus. The detection principle of this detector is the formation of the excited sulfur and the excited hydrogen phosphorus oxide species in a reducing flame, and which is obtained by a photomultiplier tube which measures the chemiluminescent emission. The optical filter can be allowed to see that emission of the light of 394 nanometer. If the emission of 394 nanometer light is seen, we understand that is the sulfur, and the measurement of 526 nanometer light gives the indication of phosphorus. So FPD is only used for the sulfur and the phosphorus containing compound. That's why it is also called sulfur phosphorus detector. Understood? FPD is also called sulfur phosphorus detector. Its sensitivity is 10 to the power 5 times greater than the organic compound. So the sensitivity is 10 to the power 5 times greater than the organic compounds. So this is a picture of the gas chromatograph in which the cylinder in which the carrier gas is there, which is having the pressure controller, and this is the flow generator. By seeing the flow rate of the gas, and this flow meter which is attached to this whole oven in which we have a sample injection system, and the next component, the column where the separation takes place, and the detector in this oven. And when all this detection takes place outside, you are able to see here, that is the recording unit computer monitor. which goes on recording into this place. So all the components are attached to this in the gas chromatograph. So this is the flow diagram of the gas chromatograph. We have seen the real picture. After that, you have all the components attached. We are not able to see in the oven in the real picture. It can be understand in a flow diagram. We have the cylinder gas, that is of carrier gas. We have this purple color which is having all the component inside the oven. We have the injection part in which we just inject our sample, and there is a this coiled column. The coiled column, we all know there are different shape of the column. Mostly used, that is coiled, that is for the large column. U-shaped column can also be used, that is the medium column, and the straight column, that is the small column. And the detectors, that is various detectors we had talked about, the detectors on which the principal works, and the recording unit. So this how it goes on recording the analysis. So if we see the working steps of the gas chromatograph, we go for filling the syringe with the sample and just see the temperature, column temperature, detector temperature, injection port temperature. So when we go for introducing the sample into the injection port, you go for noting down the time, injection time. The sample gets vaporized, and due to the high temperature of the injection port, and it's swept into the column by the help of the carrier gas. This sample component get distributed among the stationary liquid phase or the stationary solid phase. If we are using the liquid phase, it distributed depend on the solubility tendency. Means the constant which are less soluble move faster, which are highly soluble move slower. Likewise, for the stationary phase, the constants which have the greater affinity towards the stationary phase move slower, which have a lesser affinity move faster. So here if we are talking about the liquid phase, the components with the minimum solubility, that is less solubility, move faster, and those with the maximum solubility, that is highly soluble, travel slowly. The components leaving the column, it is detected by the detector, and that goes on recording to the recording unit. So the signals which are recorded according to the time required, we have the graph called chromatograph. So that is recorded, the signal which is recorded, that is plotted by under this graph, that is called chromatograph. And we have on the axis, that is the time, that is the retention time. How long the constituent remain in the column, that is the retention time. So the on the x-axis, that's the retention time we are having, and on the y-axis we are having the detector signal, and the intensity of the signal is how much, that is also seen on the y-axis, I, intensity of the signal and the retention time. So here you can able to see the 5 signals with the peaks obtained. Their resolution is very good. So by this, how we can do our analysis? We can go for having these 1, 2, 3, 4, 5 peaks, and their peaks are the different retention time in the column. As the first peak we are getting, their retention time is very low. The first constituent which is separated from the column, it is less soluble or having the less affinity towards the stationary phase, having the less retention time. So the first peak giving the idea about less affinity towards the phase or less solubility toward the stationary phase. So this elute out first, that is the retention time lesser. Then we have the retention time higher than the first, that is second peak we are getting. So that constituent is greater affinity than the first constituent or higher solubility than the first one, then the third, then the fourth and fifth. The last one having the longer retention time means it is having the high affinity or high solubility towards the stationary phase. So according to the retention time, we have the constituents, and this is our sample is containing 5 constituents because we are getting the 5 peaks. So on the basis of their retention time and the number of the peaks, we can do the qualitative analysis. So it giving it identifying the constituents present in the sample, and we have the different size of the peak. The size of the peak is different. You are able to see it is very broad, it is less broad, it is very less, it is thin among all, it is having higher broadness. So the size is different. So according to the size of the peak, how much size of the peak according to its height. Okay, the height and the size both give the quantitative analysis. The height is also, you are observing the different. So height with the size, both the thing gives the quantitative analysis. So we can do both type of analysis, qualitative and quantitative. Qualitative, how we can do, I have explained before. The number of the peaks indicates the number of the constituents in the sample according to their retention time, RT. Okay, so all are having different retention time. So depending on that retention time, we can identify our constituents. The quantitative analysis with the size and the height of the peak, the broader the size according to the height, we have the higher amount, means their concentration we can easily find out. So that we can do the quantitative analysis. So both type of the analysis can be performed in the chromatogram. Now the last applications of the gas chromatography. It is used for checking out the purity of the compounds, whether the sample is pure or it is impure samples. So to check out the impurity, we just relate with the standard samples, highly pure samples to be standardized, to be taken, and on the basis of that we can check our purity of the compounds. It is used to analyze the various drugs and their metabolites, antibiotics, antivirals, general anesthetics, chloroform, ether. We can easily analyze the various drugs. Analysis of the natural and the synthetic gases, because it's a gas chromatography. So any type of the natural gases mixture, the constituents present in the natural gas, synthetic gas can be easily analyzed. Analysis of the food like carbohydrates, proteins, vitamins, steroids can easily be analyzed. The pollutant level like formaldehyde, carbon monoxide, benzene, even DDT, these all are the pollutant level. Their concentration can be analyzed by the gas chromatography. The dairy products analysis like milk, butter, milk sugars, ketones, fatty acids, including their purity, can be easily analyzed by the gas chromatography. We have a wide variety of the applications of the gas chromatography. The volatile materials can be easily analyzed that is suitable for the volatile materials like plastics, natural and synthetic polymers, paints, microbiological samples. It is used for the separation of the atmospheric constituents, used for the refinery gases. The purity of the compound can be determined for the drugs, atropine sulfate, clove oil, stearic acid. So you have seen a wide application of the gas chromatography, and we can take the advantage of this type of the analysis for our samples. Thank you and take care.